Alrighty, we are looking at inverse functions in lesson 4.5. You can see with the objective, we'd like to find inverse functions and also determine if they exist. If they don't, then we're not going to bother with trying to find them. Alright, here's the one way we have to verify that two functions are inverses. Their composition equals x. Okay, whether it's f compose g or g compose f, if we take their composition, it equals x. We started to see this a little bit when we looked at some symmetry, that if we were to take a point and switch its x and y coordinates, that it gets reflected over the line y equals x, because this relationship is exactly what goes on with the inverse, that x and y, those two coordinate values for those coordinates, they switch places, okay, which is why we already have seen a little bit of the inverse up to this point. So let's verify right here by doing f compose g to verify that these two functions indeed are inverses of each other. Okay, so I'm going to take function f and substitute all of g in for x. Okay, now if my x value were right here and I'm substituting that in, I will then have minus 1 over 2. Now, to show this, we actually have to go through the steps algebraically to verify that this equals x. We shouldn't just say, okay, we plugged in g for x in the function f and then just say it equals x. Parentheses can be dropped because there is nothing to distribute. Hopefully you were yelling at the screen, telling me to put my positive sign there instead of a negative. Well, there you go. Next step would be those 1's will cancel, and we will have 2x divided by 2. 2's cancel, and we have x. There we go. F and g are inverses because their composition equals x. All right, now that's if we're going to look at this a couple of different ways here to find the graph of an inverse and then to find its rule. The function I have is 3x minus 2. Okay, what I'm going to do here is zoom into my graph. Okay, and I'm going to make a little sketch for 3x minus 2 by using the fact that its y-intercept is at negative 2, and then its slope is 3, which tells me to go up 3 units and then go to the right 1. Okay, then I can connect all those points, and there's my graph f of x. Okay, now let's say I want to graph f inverse without actually knowing its equation. Okay, pretty simple idea here as to what I can do. Let's identify a few of these points that I graphed, okay, for f of x. I'll keep those in blue. 0, negative 2, the y-intercept, that's where I started. And then by going up 3 and over 1, okay, I got the coordinate points 1, 1. Oh, and then I got 4, 2, and let's just throw in one more. I'll use 4 of the points. 7, 3. Okay. Now what goes on with the inverse is the x and the y switch places. Okay. So if I wanted to find a handful of points to plot f inverse, well, then let's use negative 2, 0. Let's use 1, 1. Let's use 2, 4, and let's use 3, 7. And I can just plot those points. There's negative 2, 0. 1, 1. It looks like that's where the 2 meet. Whoops, excuse me here. Back up, back up, back up. Near disaster. I got to adjust these. Okay. With f of x, okay, these coordinate points should have been 2, 4, and 3, 7. Okay. Now over here, these should be 4, 2, and 7, 3. Okay. There we go. There's the point 4, 2. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. There it is, right there. Okay. Oh, I'd say that's enough. I could connect those points. And there is a little approximation of the graph of F inverse. Okay, really simple way to do it. Just find a handful of solution points for F, switch the coordinate points, and then plot those points, and you'll get a look at what the inverse graph looks like. Now, let's say I wanted to come up with the actual equation. Then what I will do is this. The same idea of switching the x and the y. Okay, but I'm going to do it with the equation. Okay, I'll say x equals 3y minus 2, and then I'll solve for y. Add 2 to both sides. Now I get x plus 2 equals 3y. Divide by 3, and I get y equals x plus 2 over 3. I should have probably put that in red. But I'll at least label it in red that is F inverse of x. That was this graph that I already made. Okay. So a couple of different ways to look at inverses, both graphically and algebraically. Now I'm going to do the same thing with the quadratic. Okay, as far as approximating the graph. All right. Now, we're going to talk about this more in a second, but I've restricted the domain here. I'm going to plot some points for h of x. However, I am not going to use negative x values, even though I could. Okay, 4 minus x squared. Let's see if I put in 4 see if I put in 0 for x, it would be right here at 4. Oh, I'd get 1, 3. And 2, 0. I'm going to connect those. Going down just like that. Okay, that again is h of x. Now, again, I know that we could have graphed everything over here as well to get that quadratic. But I'm not looking at that part of the domain. Okay? Even though this is a quadratic, and the other example was a line, I can think about the graph of its inverse in the exact same way. I plotted 0, 4. 1, 3, and 2, 0. Now let's say I want to get a little estimate for this to get a look at the graph of H inverse. Well then let's plot 4, 0. Let's plot 3, 1. And let's plot 0, 2. Okay. 4, 0 would be right here. 3, 1 is right there. 2, 0. There's H inverse. Okay? The type of graph doesn't matter. What does is switching the coordinate points and plotting them to make a sketch. Okay? Here it works for a quadratic example as well. Okay? Now for finding the rule, that's not going to be any different. Not any different at all. If I want to find that rule for H inverse, what I would do is take x and y, have those coordinates switch places, and then I would solve. Okay? I could add y squared, and then get y squared plus x equals 4. Then subtract x. I get y squared equals 4 minus x. Last but not least, take the square root of both sides, and I get y equals the square root of 4 minus x. Okay, and it does look like from this graph, as far as the domain goes, that that graph is defined only for x values that are less than or equal to 4. Okay? Now, why would I restrict the domain? That's a little discussion we need to have at this point. Let me zoom back in on the graph. This is why. If I had plotted all these negative x values and got a graph that looked just like this, when I plotted the inverse, those would have shown up down here. And that's going to give us a little bit of an issue with our inverse function. Mainly, it fails the vertical line test, and it's not a function. Okay? Now, there's a way that we could tell to do that. A way that we could tell that that's going to happen, and we're going to talk about it more in a minute. It's called the horizontal line test. If I want to determine if my inverse is going to be a function, I would check the horizontal line test, and I would see with this quadratic, it's going to fail. Okay? It is not going to pass that horizontal line test. So what I did is said, you know what, if I want this inverse to be a function, forget about these negative x values. Just ignore them. Okay? Because if I do that, then h is going to pass the horizontal line test, because I could draw a horizontal line at any point in time, and it will touch the graph of h at only one point. With the inverse, this part won't show up, and then h inverse will pass the vertical line test and will be a function. Quick review of just kind of properties of the inverse. Okay, this is not referring to any previous function. If f of 2 is 3, f inverse of 3 is 2. Okay, this is that whole concept of the x and the y switch places. Okay, whatever x is getting mapped to in terms of a y value, the inverse is going to do the exact opposite and map that y value to x. Anytime you have a composition, f and f inverse, it'll just equal the number that you put in. If I wanted to verify this, I could break it down into two steps. Part A tells me that f inverse of 3 is 2, and then the information that was given told me that f of 2 is 3. Same thing in part C, that equals 2. Okay, if I wanted to verify that, f of 2 is 3, and f inverse of 3 is 2. All right, this is getting back to kind of a formal discussion about that horizontal line test that I was talking about. The issue with that quadratic is that it was not a one-to-one function. It didn't have a one-to-one correspondence. Okay, it had multiple x's that went to the same y value. That's why it failed the horizontal line test. Let's look at those two examples again. Okay, f was 3x minus 2. That graph looked like this. Something fairly close to that. One-to-one correspondence. At any point in time here, this passes the horizontal line test, so I didn't have to think about the domain at all. Let's slide back over here and take another look at h. If I would have graphed that whole quadratic, I would have gotten something like this. Okay? Take these 2 points, for example. 1, 3 would be a solution point, and again, this is for that graph, 4 minus x squared. And so is negative 1, 3. Now, that's okay to have two x values go to the same y value. This is still a function, okay, because it still passes the vertical line test. Again, the reason it becomes an issue is because with the inverse, okay, what this is going to end up meaning is that the x value of 3 for the inverse is going to go to negative 1 and 1, and that can't happen for our relation to be a function. Okay? So if I want to make a conclusion about this graph, h of x, that's still just about the vertical line test, and it passes, just like all quadratics do. The issue here is with the not having the one-to-one correspondence. It fails the horizontal line test. And again, the big implication for us was that if I were to graph the inverse, okay, the inverse is going to fail the vertical line test. Okay, so it's a way to tell if you have an inverse function without having to graph it. Okay, and once again, the way I went about that was to say these negative x values, don't graph them, because then this part of the graph won't show up, and the inverse will pass the vertical line test. Okay? We'll wrap up our discussion there on inverses. If you have questions, make note of those, and let's talk about them more.